The chemical trinitrotoluene, or TNT as it's more commonly known, is a highly energetic compound that sometimes finds use as a chemical reagent, but more often as an ingredient in explosive mixtures. Over time, it's become quite famous in this regard, and as a matter of fact, the explosive yield of TNT is used by much of the world as a standard unit to which highly energetic events such as explosions, volcanic eruptions, and asteroid impacts are compared. This unit is called TNT equivalent, and it's defined as 4.184 gigajoules, which is the approximate amount of energy released by detonating 1,000 kilograms, or 1 metric ton of the compound. This quantity of TNT could be visualized as a cube with a side length of 8.46 meters, so quite a lot. This unit can be given prefixes as with any SI unit or derived unit, and here you can see some examples of different explosive events in their TNT equivalent. A less precise but more useful TNT equivalent is a unit called the relative effectiveness, or RE factor. This is an index used to relate the destructive power of different explosives relative to TNT, and is expressed in TNT equivalent over mass. In my opinion, RE factor can be better thought of as energy density, and does not actually factor in detonation velocity of different explosives, or how different types of damage caused by detonation increase exponentially with a linear increase in mass. For conventional explosive compounds, RE factors can be as low as 0.32 for ammonium nitrate, or as high as 5 for octaazocubane. Applying this formula to nuclear devices results in RE values in the thousands. Anyway, I'll get more into the history and theory of this compound later in the video, but for now, I'll show you one way it can be made. Keep in mind that this process uses extremely powerful oxidizing acids, releases significant volumes of toxic gas, and produces products and byproducts that are nearly all carcinogenic. Additionally, this video is for educational purposes only, and while TNT is less reactive and more difficult to detonate than nearly any other nitro compound, it's still a chemical that must be treated with the utmost respect. Now to get started, I simply mix together 100 milliliters of 98% sulfuric acid and 40 milliliters of 99% fuming nitric acid. These acids have both been pre-chilled to below 0 degrees Celsius, as the first stage of this reaction needs to be kept as cold as possible. This nearly anhydrous mixture of acids is called a nitrating mixture, and will provide the nitro groups to the trinitrotoluene. Once these were thoroughly mixed, I next set up an addition funnel containing 35 milliliters of toluene, and began to add it to the nitration mixture dropwise and under constant stirring. This will result in a color change along with a massive generation of heat as the first reaction proceeds. This first reaction specifically is a mononitration of toluene, which is highly favorable and thus extremely exothermic. Because of this, it's extremely important to control the temperature of the reaction during this addition, as excessively high temperatures will cause the reaction to switch from a nitration to an oxidation. This is referred to as a runaway reaction, which will not only destroy your product, but can be extremely dangerous as it will quickly generate large plumes of toxic nitrogen dioxide gases. Through test tube scale trial and error, I found that the transition from nitration to oxidation occurs around 90 degrees Celsius. So just to be safe, I would recommend keeping the mixture well below 75 degrees Celsius. Anyway, when toluene is mononitrated, it will form one of 3 possible isomers of mononitrotoluene, or MNT. These particular reaction conditions tend to form the ortho and para isomers in a 2-to-1 ratio, while the meta isomer is unfavorable and only forms in small amounts. This is quite fortunate, as the meta isomer will result in the formation of unstable isomers of TNT, which will have to be removed later on. Now, once all the toluene has been added and the mixture allowed to react for another 30 minutes under constant stirring, the reaction is complete. In industry, the MNT would now be separated, cleaned, dried, and added to a fresh batch of nitrating mixture to add the second nitro group. However, nitrotoluenes are very toxic, and so to limit the possibility of exposure, I measured my reagents at the beginning to allow the first and second nitrations to be done in a single step. Doing it this way is a bit less efficient and somewhat raises the risk of a runaway oxidation. However, combining the first and second nitrations isn't nearly as inefficient or dangerous as combining the second and third nitrations, or worse, combining all 3. Regardless, to begin my second nitration of toluene, all I had to do was slowly ramp up the temperature of the reaction by about 5 degrees Celsius every 5 minutes, until the temperature was between 75 and 80 degrees Celsius.